Okay, good morning. Let us resume our discussion. So what is that we were discussing in the last class? Can any of you tell a couple of points?
We started discussing about feature extraction in images, and we saw whether we can extract features for the whole image, or we can search for bigger pictures and take region of interest, ROI. And then we started with the feature extraction on whole image. We saw three types of features: gradients in X and Y direction, histogram, and shape-based features. Well, then we also discussed about ROI kind of features, where we saw corner detection, local histogram information, and HOGs. And then we ended the discussion with on convolution and filtering.
Very good. Good. So at the end of previous class, we have seen that if you would like to highlight some features like edges, we can design the filter or the kernel such that it also looks like an edge. Okay, so for example, if you convolve with a filter, which is, say, edge means what? Sudden transition. So as you can see, if I just give you three filters, okay, if I ask you, okay, what are the characteristics of these filters? Say one filter is like this. Assume that its filter is 5 samples, 0, 1, 2, 3, 4, okay, 5 samples. Fine. This is the filter one. This filter, say H1 of n. Okay. This second filter H2 of n. I'm just writing here. Okay, that is like this. 1 minus 1. Again 1 minus 1. Okay, and then 1. Oh, this is again 0 to 4. 1 minus 1. Okay, this is all 1. Third filter H3 of n. Okay, so it's like this. So it's 1, just minus 1, and then 0 else. Assume that this is the filter. So if I give you this kind of filters, or if I give you, I can give a series of filters like this. What kind of features does this extract? If I perform a convolution with this, with respect to the image, say image also let us consider in 1 dimension. Because usually you can consider image in 2 dimensions, but let this be a signal. Okay, in 1 dimension. So this 1-dimensional signal may have actually many things. Though I'm sketching it as a continuous, otherwise we can sketch it as a discrete itself. Okay, so this is like this. It may have any arbitrary okay, assume that this is the rough signal. Okay, S of n, 0 and then some values. Now, if I want to highlight wherever there are sudden transitions, okay, or wherever there are some kind of edges, as we see in 2-dimensional images, edges means what? So it is intensity changes. Okay, this is all white and this is all black. Okay, it means that there is an intensity change. Again, here in between, if it is white, okay, and then this in between here is black. Okay, there is again intensity change like that. Okay, so wherever there are intensity changes from across the pixels, that we consider it as an edge or high frequency in terminology of the frequency domain. Okay, high frequency means what? High variation. Okay, variation from sample to sample is high. Okay, so that is referred to as edge in images, or the sudden transition of intensities in images. Now, if I want to pick them, okay, so just to simplify this discussion, or to give a more clear, much distinction among the filters, I just even modified the third filter. Now, given these 3 filters, which will give me edges, okay, which will highlight me uniform regions, which will highlight me corner points, or corner points means it's in the variance from the neighborhood of samples is very high, in the sense that so far they may be all black, suddenly there may be some white pixel that might have appeared. Okay, just suddenly, I think here actually you can see that. So this is all black. If we assume, suddenly you have a white pixel here. Okay, similarly white, in between white you may have a black pixel. Okay, like that. This is the this is referred to as corner point in our cells. In our terminology, even this corner point can be like this, wherever there is a sudden transition with respect to the neighborhood. Now in this signal S of n, Okay, which filter H1, H2, H3 will highlight, say, uniform regions. So I will just orbit little, which will highlight edges, which will highlight uniform regions, which will highlight corner points. When I perform convolution operation. Okay, so the operation that I perform, this is between S and H, is convolution operation. So Y of n is equal to S of n convolved with H of n. Any Hi of n. So H of n means H1, H2, H3. What does convolution do? As you have seen, convolution means you put this filter on this, okay, at any location. And from here to here, if it filter comes, okay, if I just put around this point, and then filter come from here to here, then what I do? I perform element-wise multiplication with the samples here, okay, sum them, and then put the value at the center. Those who know about signals and systems are very familiar with convolution. Those who are new to convolution, you can easily relate it as the kind of correlation. Okay, correlation also exactly does the same as that of convolution, except that correlation directly puts this signal on this and then finds out the element-wise product and sum the value to give at the center. Convolution, flip the filter and then put it. That's only the difference. Flipping or not flipping is the difference between convolution and correlation. Here, flipping is not very important because most of the times we are interested about the features as a description. So whether this description comes in this direction or that directional aspects doesn't come too much in feature extraction. So you can consider now correlation itself. Okay, those who are familiar with correlation or you all are familiar with correlation. That means correlation between two vectors, as you know, putting this vector on this at this location and then element-wise product between this vector and this vector, and then the sum being written at the center. Okay, that's how the correlation of signals or the vectors put at this location is done. Okay, if I want to perform correlation at this location, I will put whatever is the filter here. Okay, and then I will perform like element-wise operation between the signal here and this filter here, and then put at the center. That's the correlation operation. So you can understand correlation, and convolution is a operation which is actually a flipped version of correlation. Especially in signals and systems concept convolution comes because usually the output of any system, okay, if you want to compute, if you have a system described by some filter response, okay, or impulse response, the input is given as Fn, and then the output, if you would like to get, it's equal to, as many of you know, convolution between S and H. Okay, so this naturally comes from the signals and systems concept. In fact, the convolution neural network, in convolution neural networks, convolution also has come from signals and systems concept only. Okay, fine. So given that, now to make you understand, you can also consider it as correlation, as I mentioned. Okay, fine. Now the question is, which one among H1, 2, 3, which one will give me edges? Can one of you tell? Which filter, if I convolve, will highlight the edges? Any answer?
H2 of n.
H2 of n, very good. Why does H2 of n gives edges? Any reason?
Because you can see there are sudden transitions in H2 of n.
Right.
So when it will cross over the signal, so it will definitely give those changes.
Right. Essentially, as I mentioned, convolution and correlation are same, okay, except for flipping. Now, if I just don't too much bother about flipping because it's also symmetric. What happens? Correlation does between try to find out similar patterns in a signal. Okay, so what we are doing here is to find out a similar pattern. This itself is looking like a wavy nature. Okay, as you can see here, if I start from here, okay, it's like this. Is it not? So it's a kind of a wavy nature I'm trying to find, and wherever that wavy nature kind of signal is encountered, it will give a high value. That itself is an indication that I have identified that. Similarity score between this and that will be high. If I want to highlight the uniform regions, then which one I have to consider? H1, H2, and H3. If you would like to consider uniform signal, which one should we consider? Yeah, I need an answer.
H1?
Yeah, H1. Because it's natural that it will highlight the uniform regions. Whenever there is uniform regions, its correlation is high. See, if I put the same H1 here versus here. Okay, if I just perform here, what is the sum or the correlation sum? So if we assume that I just bring the H1 here, okay, and perform correlation. Okay, what is the value of correlation? Can some of you tell? I just put at this location, okay, and then perform the correlation. And then what is the correlation value here in the output signal? A quick answer is welcome.
0.
Yeah, very good. Okay, the answer is 0, is it not? The value of it is 0. Whereas if I perform correlation by putting this uniform filter here, okay, then its value will be what? Here.
4. No.
It is answer is how much?
3.
Yeah, very good. So its answer is 3. Okay, because actually if you just do a 4 minus 1, that is 3. Hope you people understand how I am writing these things. This is very important. See, I can directly switch over to the discussion on the topics which will more like a computer science kind of point of view, but this will give us a good understanding of how exactly the feature extraction is happening. Okay, and also later in convolution neural networks as well, the deep neural network structures are very computationally intensive. You will have hundreds of layers, in fact, thousands of layers. And then you have at each layer several parameters. So millions of parameters and then hundreds of layers. The complexity of the networks are the algorithm, like the architectures we use are very, very high or bulk. So their understanding is not very easy. If you understand at this level, then the things will simply scale up because the nature is there just replicating the same thing again and again. So if you understand one block, then you can understand the whole thing. But if you don't understand the single block, I think you are all black box. Okay, as many people say it's black box, still it's a full complete black box. Okay, nothing else. Okay, so understanding these basic things are important. So now, as we mentioned, if we put the uniform here, its value is 3. So the right. So similarly, you can calculate. If I put, for example, instead of uniform, if I put this H2 here, okay, at the same location, H2 if I put, what is the value? Oh, you can calculate. Can some of you, some other student tell? If I put instead of H1 here, okay, if I put H2, instead of H1 of n, if I put H2 of n, okay, what's the value at this location? Just to give an example.
0, sir.
Okay, is it 0? So 1, so it's actually 1 into 1 plus minus 1, 0. Okay, and then again plus 1, minus 1, 0. And it is, what is total value? It is minus 1, right? Correct. Yes. So these two are becomes 0, and then up to from here to here it becomes 0, and then this will be only left with multiplied with positive value here. Okay, this is multiplied with this. Okay, this is multiplied with this, and so on, right? And this will be left with this, and that is minus 1. So finally, minus value is minus 1. Like that, you just exercise. Take the signal and then find out the say this is what I have written here is S of n convolution with H1 of n. Okay, what I would suggest is just take the same signal. You take actually 1, 2, 3, 4, 5, 6, 7, 8, 9, okay, 10, 11, 12, 13, 14, 15, and 16. Okay, do it just as an exercise. What is the convolution of S of n, or correlation or convolution? You do either way because this flipping doesn't matter here, all are symmetric. Okay, and then S of n convolution with H1 of n, what is it? And then S of n convolution with H2 of n, what is it? And then similarly H3 of n. H3 of n has a simple characteristic. So can one of you tell what happens if I convolve with H3 of n? If I convolve with H3 of n, what do you think will happen? One thing you need to notice, I am centering at this location and writing here. Okay, so ideally my indexes here, okay, are not 0 to 4. Those who know a little bit of convolution operations better can easily guess. So it's -2, -1, 1, 2. This is how I am writing. I am centering this also, so that actually things will be, I am putting it at center and then finding out. Okay, fine. So now tell me, if I convolve with this H3 of n, what will happen? Or correlate.
Same signal will come, S of n.
Very good. Same signal will come because it's like a unit impulse, those who know that. Okay, so what I'm doing is I am putting at the center and then multiplying with that and writing the same thing. However, as I previously have done, so if I have something like this, okay, 1 here, -half. In that case, it highlights the like the corner points or the points that are distinct from the neighborhoods. Okay, so this point will be very well highlighted. Okay, similarly, there are few other points. This also point may be highlighted because this is a sudden transition. Not only in one direction, but also in both directions. Such things will get more, this one will get more highlighted. Okay, rather than this one. Okay, the value will be high positive direction in high positive or high in negative. Okay, either way we say that it is highlighted. Okay, so this, after highlighting those things in the convolution, I may threshold it to identify the regions of interest. Okay, so hope this is clear. Any questions on this? Okay, so essentially, if you would like to identify a particular feature, like particular shapes or particular features, we should construct the filters in that way. Now, just to give you a little more intuition on this, now assume that I have a scenario wherein this is an image. Okay, now let's come to the image. I want to identify, okay, this kind of shapes. Okay, it may have something like this, and then somewhere here. Okay, assume that this there are several other shapes, but I just want to highlight this kind of shapes. Now I want to have a kernel or a filter here. Okay, I may just denote with some k in 2 dimensions or even w. So any notation is fine. Let this be a 5 cross 5. Okay, the question is, how should be this 5 cross 5 to identify this kind of shapes? Okay, any guess on that? Then shape 1 I will say, shape 2 and shape 3. I just want all 3 shapes subsequently. So let the shape 3 be a little more simple. This kind of shape. Okay. So any idea on this? For identifying shape 1, how should be the filter? I am writing here. The filter should be like this, remaining all being zeros. Of course, it is 5 cross 5, right? So we will have actually. So of course, we can also have 5 cross 3 if it is 5 cross 3 dimension. It is to the scale of the object we would like to find. Okay, otherwise we have to take this at different scales. So down sample, up sample version, and so on, and then convolve there. So this is a typical, this is one example. Other example is 1, 1, and then again 1, 1, 1, 1, 1, 1. I am not like, you understand, right? It's not a decoration, but it's like a kernel I am writing here. Hope you got the point, how I am writing this. Yes or no? So this is 5 cross 5 kernel. So now the next question is, assume that if I want to capture this kind of shape. Okay, S2. How should be the kernel? Any guess? Yeah, I need some answer now. How should be the kernel to capture this captures triangular shapes?
Dimension, sir.
Yeah, please.
No. What should be the dimension we should choose?
Yeah, let it be 5 cross 5. And we need to capture now rectangle squares. How should be the filter? With this filter, what we do, this is anyway an image. Okay, what we do is say if we want to highlight these shapes, the output will be equal to I convolution with, in two-dimensional convolution, we will show that with W, or correlation you can consider, since these are all symmetric. Okay, of course, this is not symmetric, but you can consider correlation or convolution. For time being, correlation itself you can consider. Correlation we denote with this. Right. So now tell me, how should be this shape of this? Yeah, please tell.
First and last column and first and last row are one. Remaining all are.
Very good. It's like Rangoli now for us. You keep all rest zeros. Right? I missed one more row. I think it's fine. Okay. So like this. So you can see that if you convolve with this, it will highlight the rectangular or square shapes. So how are we picking the filter? It determines what kind of features we want to highlight. Okay. And convolution is the process of highlighting such features. Okay. Hope this is clear to you. And if I want to do this, say assume that this is a big, okay, this is I have written, but I want to highlight these things. What should be the kind of kernel? That's all you put actually like this, or you can also put even bigger and then put the rest of the things 0. That's all. Okay, and then rest of the things zeros. Right? I think we are going somewhere. Okay, so essentially the idea I hope is conveyed. So we need to have the filter looking like the shape we would like to recognize to highlight such features in the output through convolution. Okay, so now let us see some of these aspects. Let us see now through some of the visual details. Let us understand this in how exactly we use in computer vision. Before that, we will see actually how exactly these are developed in image. Yeah, if you have any specific question, you can ask. Otherwise, we will move on with the discussion. Please mute in case if you are not conveying anything to me. Okay, so the details for discussing this interest point localization and then feature extraction, I have taken from Professor Mubarak Shah video lectures. So he has given a video lectures on computer vision. They are very famous or well known. You can see them at this YouTube link. And there are some discussion on the feature extraction by HOZ from Professor Jitendra Malik. That also I have considered for discussion. So the basic features that we have discussed in images are image histograms, which probably you might have, we already have discussed, and you might also have seen in other courses that they describe the global features of an image. Okay, so overall, how is the intensity variations that is being conveyed by image histograms? Okay, so it will tell what information does it give. It gives, is it a low contrast image, high contrast image? Are there white and black regions? Okay, if you consider color histogram, it will also tell what color is dominating. Is it red color dominating or blue or green and so on? Okay, so for classification purpose, color histograms may be more useful. Even the grayscale histograms are useful to some of the problems, especially where you have actually the high contrast defining the different classes. Then the next discussion that we have brought in for feature extraction is through correlation or convolution. That is a kind of neighborhood operation in image processing. What do we mean by neighborhood operation is if we would like to infer something about a region, what we do is we do not only look at the center pixel, we also look at all the neighborhood pixels and then infer. Whenever we consider in image processing or image understanding, there is no understanding for a pixel. Okay, point doesn't mean anything. Okay, in a scene, point doesn't define many things or anything except if the case of point targets and so on. In very rare cases, the point defines nothing or a pixel defines nothing. The patch defines something. The inference has to be made based on the patch surrounding a pixel. Okay, so with the neighborhood information, we assess the center of the neighborhood. That's the region, center of the region is being defined by its neighborhood. Okay, so and not by a pixel. That we should remember. And usual way of highlighting the information in a region through neighborhood operation is through convolution. Okay, that's what we have discussed so far. Okay, and then the process of doing convolution can be done like with different filters. How do we define filter? We have just discussed now. Whichever you want to highlight, based on that we define the filter. Okay, so the process of convolution in 2 dimensions, you can see here. How is that done? So you can see, as you can see here. So if you have a filter W00 and then the all elements of filter, this is a flipped filter. Sorry, this is -1 comma -1. This is 1. So here you can see that what we are doing is we are multiplying with this. So essentially it is not very. So if we start with W1 comma 1 here, then it is a flipped filter. Okay, and then what we are doing, we are finding out the element-wise product by placing a filter at the f of x comma y. Okay, and then that element-wise product will give us the modified version of f of x comma y or g of x comma y. If we write this as f hat of x comma y, f hat of x comma y, which is convolution of f, okay, with the w. Okay, so this is a 2 dimension, this is also 2 dimensions, please note. And in convolution operation, what happens if the image is of bigger dimension? Okay, we will not perform this element-wise product only at a single location. Okay, but we perform this at several all the locations of the image. That we have to remember. So initially the filter will be placed here. Okay, so then it will be placed here. Okay, in fact, at each pixel it can be placed the filter, and then you perform this element-wise product, sum them and put at the center. The output will be f hat. Okay, the convolution output. Hope this is clear, right? As I mentioned, if I want to perform, if I want to highlight uniform regions, okay, what we mentioned is you can convolve with, say in 2 dimension now, if I want to perform or highlight uniform regions, what kind of filter do you suggest? So now the question is, say in 2 dimensions, we want to design filters and we want to highlight the uniform regions in 2 dimensions. What kind of filters should we consider?
All ones, right?
Yeah, all ones. But usually if I perform with all ones, a convolution or a correlation operation on an image, what happens? What is the limitation? If I perform in a region, say the usually intensities in this region vary from 0 to 255. Okay, if I perform with all ones, assume that all intensities are 255 in that image. If I perform this correlation, and what will be the value at the center now? If all the intensities are 255, if I perform a correlation operation with this kernel 1111, okay, all ones, what will be the value at the center? Or what is the result of the correlation? What will it be?
255 multiplied by 9.
Very good. 255 multiplied by 9. So, but the intensities we would like to have only from 0 to 255 in images. So what should we do now? How should be the filter now? Or the modified filter or the final filter for
Divided by 9.
Yeah.
Normalized by 9.
Yeah, highlighting uniform regions, it is 1 by 9. That's all. So we should make sure that the range of the output is also 0 to 255. That is an important aspect, because the processed image should not look completely different from the original image. Only we can see based on the neighborhood we are processing to highlight some of the aspects. Okay, now what is the other possibility? if I don't want to have it actually as a uniform filter, but still I want to highlight the uniform regions, or I want to highlight the smooth regions. Okay, I want to otherwise knock off the noise. So the other way of saying highlighting uniform regions is, if I have sudden noise somewhere, I just want to knock that off. I don't want to highlight it. Okay, I don't want to highlight non-uniform regions. In such case, how should be the filter? Any choice two? This is choice one. And what
Median
is the
filter.
choice? Oh, it is. Okay, what is the choice two?
Median filter.
Okay, median filter. Why are you saying median? Median filter, as he mentioned, what does median filter does is, if I apply a median filter in this region. Okay, so what it does is, if I apply a median filter in this region, it takes all the pixels, okay, in this region, and arranges them, say in a, it sorts them, the pixel values, and then takes the, after sorting, the middle value. Okay, so if I sort all the values, all are zeros, assume that this is only like 255. Oh, so let me see if I can write this with better. So here 0 to 20, 25, 0, 0, 0, 0. Okay, and then 0, 1, 0. Assume that all values are close to 0, only one value is 255. If I perform a median filter here, what does it do? It will knock off, say, if I perform even here. Okay, so assume that this center. So if I perform a median filter here, what does it do? It will, the median of it will be in this region. If I perform median filter, what is the output? The median filter, what it does, as I said, it sorts and then takes the middle value. It will be
25 replaced by 0.
Right, 25 replaced by 0. And hence it knocks out the noise. This is one way. But median filter is a non-linear filter. In sense, it's not a linear convolution operation. Okay, of course, you can also do that. That's one possibility. Any other linear convolution in linear filter that will also highlight the uniform regions, or avoid the non-uniform regions, or suppress the non-uniform regions, smooths the non-uniform regions. Any other suggestion for that kind of filter? Say, assume that if I put somehow the value here is 1, okay, and then 0.6 or 0.6, 0.6, 0.6, okay, 0.4, 0.4, okay, 0.4 and 0.4. Okay, of course, this doesn't sum, so I will sum to 1, okay, sum of all elements. Otherwise, I will decrease this also. So assume that I normalize, okay. But this kind of arrangement, it looks like a Gaussian. Okay, as you can see, more importance is given to the center pixel and less importance is given to the neighborhood pixels. That kind of filter is referred to as Gaussian filter. That also helps us to smooth better. Right? So that you can see in the next slide. So you can see this is a good averaging filter and this is a Gaussian filter, or weighted averaging filter, kind of close to Gaussian filter. Okay, this will highlight the uniform regions. Now the next, so if you see, actually, if I perform a smoothing operation on this image, as you can see, so there is a subsequent blur or smoothing happening. Here there is no noise, so you can't really see or appreciate the advantage of applying uniform filters. But however, if you have some noisy details, okay, then you can see that the applying uniform filters, okay, will knock them off. Okay, so that's the advantage of uniform filtering. So essentially, these will be used as a part of feature extraction or highlighting the features, okay, in subsequent discussions. Okay, assume that there are other operations in image processing, which even thresholding, for example, if you just threshold above an intensity, that's again like a median filter. This is also a non-uniform filter. Okay, you just put a threshold, more than this threshold, you put 1, less than this threshold, you put 0. That also can be operated as a filter. You just sort them, the values in the region, and then if the values are above some threshold, you put 1, below the threshold, you put 0. Okay, so that's also can be modeled as a filter. But however, it's a nonlinear filter. Okay, this is a pure Gaussian filter, as you can see. Okay, as the expression in Gaussian in 2 dimensions is like this. Hope you people have seen this in other courses. This is the Gaussian filter. How do we construct? So in fact, a multivariate Gaussian filter can be written as, so if in 2 dimensions, okay, 2 root 2 pi, and then covariance matrix if we consider, okay, mod sigma, where covariance matrix is in 2 dimensions, that is sigma 1 square, sigma 1 2, sigma 2 1, sigma 2 square. Okay, that means if you have any information in 2 dimensions, in this direction, x direction, you will have actually one variance, sigma 1 square or sigma x square. In y directions, you will have other variance, sigma 2 square, and there will be some covariance, sigma 1 2. Given all this, you define a covariance matrix, okay, for the data, that is sigma 1 square, sigma 1 2, sigma 2 1 or 1 2, and sigma 2 square. Based on this covariance matrix, we write the Gaussian distribution, and that helps to write the filter also. Here we assume that in x and y directions, the variance is same. That's why we have written sigma 1 square equal to sigma 2 square equal to sigma square. Okay, to simplify this, further sigma 1 2 is equal to sigma 2 1 equal to 0. There is no covariance. In such case, you can simplify like this. Otherwise, you can write this Gaussian expression. This you will see much more details in the other classes, in like probably MLIP class or somewhere. 1 power half. Okay, so where mu is the mean vector, mean in direction x1 and then x2. So x is a vector in x1, x2, and then mu is a vector in mu x1, mu x2, mu1, mu2 you can consider. Okay, just for simplicity of notation. I hope these details you will get little more later, but in maybe in other classes. But the main important details here is 2-dimensional Gaussian. Essentially, if we consider the case, special case where the variance in both directions are same, and then the covariance is 0, turns out to be what is written here. Okay, and then this one is useful for constructing the 2-dimensional filters. Of course, in this course, we don't construct the 2-dimensional filters and use them and so on. In image processing course use. This is for information. And subsequently, discussions you can interpret or understand better with the background of this. Now, for as I mentioned, for noise removal, you can apply averaging filter, you can apply median filter. Okay, and then you can also apply the Gaussian filter, as we discussed. There are different kind of noises that also you get more introduced in image processing. One kind of noise is adding Gaussian noise. Okay, so around mean value of 0, and then with some variance we will add. Other way of adding noise is just salt and pepper kind of noise, where we inject randomly some dots, either 0, suddenly putting 0 values, or suddenly putting 255 values. That is referred to as salt and pepper noise. So different kind of noises usually can be treated slightly differently. But however, now given the deep learning, also most of the things are now learned themselves, in the sense that we don't specify what filter we would like to use. We will allow the network or the algorithm itself to learn itself what kind of filter should we consider. This W, so far what we are defining by different, here W is like this. So by different domain understandings, later we will not define it. We will try to learn driven by the objective function we would like to achieve. Okay. That's the main difference between the way how the image processing and conventional computer vision has been dealing versus the deep learning or the machine learning deals with the solving of the problem. Now in 2 dimensions, if you would like to highlight edges. Okay, so what kind of, what suggestion, like what kind of filter should we consider? Any idea on this? So now we assume that we would like to now highlight edges in 2 dimensions. Enhance edges.
Middle row should be 0.
Okay.
In the first row, middle value is more weighted than other.
Yeah. So one possibility is just simply 1, 1, 1 on the top row, 0, 0, 0 in the middle, and minus 1, minus 1, minus 1 in the bottom. So what it does, so whenever I convolve in an image where there is a horizontal edge, okay, so this will highlight this because the like you see that this is all white, this is all black. Okay, then what happens? The difference will be very high when I convolve with this. In 2 dimensions, it is not enough just to define a horizontal edge, but we also need to define separately we need to take care of x direction, 1 direction, and as well as y direction. So we may have actually 1, 1, 1, 0, 0, 0, minus 1, minus 1, minus 1. Okay, this also can highlight the vertical edges. Putting together, this will give the gradients in x direction. This gives me gradients in y direction. And then the overall gradient g, if I want to get root of gx square plus gy square. This is the magnitude of the gradient, while the angle of gradient is being given by tan theta, tan like is given by what? Gy by gx. Or the theta is given by tan inverse of gy by gx. Correct? Angle of edge is given by tan inverse of zy by gx. What is zy gx here? Say if there is an image I, for which I would like to highlight the horizontal edges. Gx is obtained by finding out the convolution of I with the w in x direction. Okay, this filter, if we define wx, and then this is wy, okay, and then gy is obtained by I convolve with wy. Right? So if we convolve with the y direction filter, you will get the y directional gradients. Okay, so these are the gradients in x and y directions, right? Okay, so the other way of defining this is, so why say now a question, say if I swap between 1, 1, 1, 1 here and minus 1, minus 1, minus 1 here, is there any problem? So instead of like this, if I just put this row as this and this row as this, okay, is there any issue? Do I get the gradient in x direction or not?
We can get, sir.
We can get. Okay, so now the next question is, instead of writing 1, 1, 1, I put 2 here in between. Okay, is there any issue?
No, sir.
No, the reason is usually what will happen, this is the center pixel, and the pixels near to that pixel, we assume that they give more information about that pixel. So if I want to identify whether there is a gradient at this location or not, what I consider is, say I would like to see the pixels surround it more than the other pixels. That is the reason actually we can also consider 2 here. Okay, so that actually these are the nearby pixels. So if I put instead of this value, if I put this value 2, is there any problem? So if I put instead of this, if I put 2, 2. Oh yes, the reason is this is not the closest pixel. Okay, which we would like to highlight. Okay, which we would like to see with respect to the center pixel, this is far away pixel. Okay, so we cannot give more importance to this compared to this, right? So further, if I put only one of them 2 and then one of them 1, is there any problem? Yes, I assume that I have put only one of them 2 and the remaining, say this one I have put as 1 only. Is there any problem?
Yes, sir.
Yes, the reason is what? What is the reason? If I want to say I define now a edge like edge kernel, something like this. 1, 2, 1, okay, 0, 0, 0 again, minus 1, minus 1, minus 1. What is the problem with this? Edge kernel. This is the next direction. Assume that you have actually a uniform region. Okay, this is all uniform. In uniform region, if I apply this filter, okay, convolution with this filter, what should happen ideally? Say an edge filter, if I apply in a uniform region, I only want to highlight the transitions or changes. If there is no change, the response has to be how much? If there is no change, constant signal. Okay, I only want to highlight the changes. Okay, and then if I am applying a filter, if it is a constant region, the output of that filter should be how much? Convolution of that filter with the signal should be how much in the constant region or uniform region? Should it be constant value? Or should it be zero value? I don't want to highlight anything. It's an edge. Okay, so if you have a signal like this, okay, and then only when transitions are there, I want to highlight. In a constant region, whether it be, say, this value or this value or this value, I want only zero value to be outputted. Okay, so uniform region, it has to result as zero value as output. But if you convolve with respect to this W, okay, you will not get the zero value as output. What you get will be a non-zero value. That is the problem with this. So it's not a good kernel. This is a good kernel. Okay. So hope you got the point. So now, as we discussed, the filters can also be filtering, or the convolution can also be used for highlighting the transitions or the sudden changes. So the typical filters as defined in image processing are say this robot filter or pivot filter or Sobel filter and so on. The names are given like this, whichever we have discussed so far. For them, the names are given like this. Okay. So each of them, if you see, the sum of elements in this will be zero, making if they are applied in uniform region, the value of the output of the filter will be zero for any edge kernel or edge filter. As you can see here, it highlights only edges and zeros values in the uniform regions. Okay. And as I mentioned, these are the x directional filters. Okay. And then bidirectional filters, and convolution with x direction filter will give me gx, gradient in x, I convolved with wx. Okay. And then gy, gradient in y. In fact, I can write the capitals even here. Okay. Gy, and then gradient in y. Okay. I convolution with wy. And then using both, I extract the overall gradient gx square plus gy square, where all are element wise operations. Please note that. Okay. And then theta, angle of the edge, that is tan inverse of gy by gx, again element wise operation. All are element wise operations. Okay. At each element, I get the magnitude of edge and angle of edge. If I have an edge image like this, okay, which is 100 cross 100. Okay, from this, what I do, if I apply with the convolution and so on, if finally what I get, the gradient information, which is also of same dimension as that of the original image, and then the angle image is also of same dimension at each pixel, giving the angle of edge at each location. Hope you got the point what I have been discussing. This you can get the magnitude of edge and then the angle of edge at each pixel. Okay, this is also 100 by 100. Okay, this all can be done through process of convolution and a set of operations after convolution. Okay, with this you can do several other things. You can have the base information and then sharp, like give more importance to the edges only. That is referred to as unsharp masking. Okay, so you unsharp regions you mask in some sense, and sharp regions you highlight. Okay, so how is it done? Just simply add the some previous, like the original image with respect to the gradient information. Okay, so that gradient regions, high gradient regions will get more value. So as you can see, this looks more sharper than this image. So you can also highlight the corner points. Corner points means what? Say in an image, if there is a blob kind of points, okay, suddenly there is a black spot. Say in iris, for example, you may have a white spot. Okay, but if you see in red blood cells, you may have a black spot in red blood cells, especially when there is a parasite or malaria or infection. Okay, so the parasites will be formed. Those parasites will have on a red blood cells, RBC. Okay, you have actually, or the whole thing is like it looks like red, but there is a black spot. Okay, that's actually a parasite in RBCs. And then this in, say, if you consider an iris, image, there will be a white eyeball. If you consider, there will be a white spot. Okay, so there are different applications where you need to highlight these spots. Also, as we mentioned, the key points, if you would like to understand in an image, the key points are those, even for a person or whatever, the key points are those where the intensity variations from the neighborhood are very distinct. So those also can be highlighted by two-dimensional derivative. So if you see Laplacian of Gaussian or the second, say Gaussian is a smooth operator. Okay, as you can see, Gaussian looks like a smooth curve. Whereas this first derivative of Gaussian, if you look, okay, it looks something like this. This first derivative of, this is second derivative of Gaussian. So first derivative of Gaussian, how does it look like? Can somebody guess? First derivative means what we want to show is this variation or slope of this first curve. Okay, this is Gaussian, dz by dx, if we are considering this as x. Okay, so how does the Gaussian first derivative looks like? The slope is first varying well and coming to 0, and then the slope is going in negative direction and then comes to small. Okay, this is the first derivative. Second derivative of Gaussian, d square by dz by dx square. How does it look like? Okay, as you can probably again slope of this curve. So it looks like this. Okay, this is the second derivative. Okay, so I have plotted first, second, and third derivatives, which you can analyze a little bit with your understanding. So those second derivative, if you see, suddenly there will be, in fact, it will be much more peak. Okay, compared to these two. So as you can see, -8, which is a very big negative value among the several positive values. That's how the second derivative is. -4, okay, 1, 1. Okay, if I just put in one dimension. Okay, so it is -4, 1, 1. This is the second derivative in one dimension. In two dimensions, this is the second derivative of Gaussian or Laplacian, it is referred to as. Okay, so essentially it is highlighting a point targets or point corners. Okay, this highlights the corners. So we will stop here. If you would like to convolve, if we convolve with this kind of filters on an image, we highlight the corners. So this is referred to as Laplacian. It highlights essentially the corner points, as you can see here. Okay, these are the points which are highlighted. So I will stop the discussion here. In the next class, we will discuss more on how exactly we localize to the features and what are the other descriptors for the features. Thank you.